All right, let's talk a bit about sports science application. And in this case, we're going to look at running economy. So I had a professional triathlete reach out to request some testing of 3 different shoes this athlete was considering to race in. They're all the shoes are advanced footwear technology type shoes or super shoes. There's similar types of components, but each unique in their own design. The actual shoes aren't important in this presentation, other than knowing that the 3 shoes were super shoes. And so this athlete wanted to know a little bit about running economy or rate of oxygen consumption when running at race pace, and if one shoe stood out. Well, we talked about it, and we said, here's the deal: is that the influence of the shoe will likely be quite subtle, and we'll be interested to see if we can detect any differences between the shoes. But we may be able to rule a shoe out that may be underperforming in terms of running economy. So we talked about a design of the experiment, talked about some of the just the parameters that we would use, and some of the measurements we would take. And so in this presentation, I want to talk a little bit about that, and talk a little bit about the results, with giving the sense of how in sports science we use physiology in this case to help an endurance athlete. So a couple terms that we need to have in our toolbox, our sports science toolbox. The first is running economy. I've already mentioned this term, but it's important to define it. Running economy is the rate of oxygen consumption for a given speed, and the units we use is mLs per kg per minute. It's a rate. It's a rate of how fast oxygen is being used to do something. In this case, we're talking about running. Another way to look at running economy is it tells us how fast calories are being used, what rate calories are being used. And so we can do the math between mLs per kg per minute and ultimately to calories as well. But it's how fast calories are being used for a given intensity. The other term that we need to be familiar with is energetic cost of locomotion. This is defined as the amount of oxygen consumption for a given distance. In the units, we can actually use mLs per kg per distance, or typically we would use liters per distance, whichever way. But in essence, it's volume of oxygen for a given distance. So how much oxygen we used to run a mile, how much oxygen we used to run a kilometer, how much oxygen we used, the total amount to run a marathon. In essence, this tells us how many calories are being used per distance, or just as an example, per mile. 100 calories per mile, or how many calories over a marathon or a half marathon, or what have you. These two terms are mathematically linked, and you can derive one from the other for the most part, but they each give us a unique perspective from a physiological perspective in terms of running. How fast oxygen is being used, how much oxygen is being used will actually tell us some different things about running performance. So I always like to use this model to sort of give a framework for what we're doing in this type of test. So in our body, we have chemical energy, stored potential chemical energy, carbohydrates, fats, proteins to some extent as well. And our body is designed to transform that chemical energy to mechanical energy. Mechanical energy being energy of movement. We have kinetic energy, we have potential energy, we have the ability to move or apply a force over some distance, and therefore we have movement. So it's a neat little model to talk about what's really happening in the body is we're transforming chemical energy to mechanical energy. How do we do that? Well, we have 2 metabolic pathways, aerobic and anaerobic, and that's in this middle column right here. And both these pathways are active pretty much all the time. But what we might want to do for certain sports is understand how well the aerobic system is transforming chemical energy to mechanical energy, or how much it's being used. Or we might want to know how much the anaerobic metabolic pathway is active during some type of activity. Because both of these are transforming chemical energy to mechanical energy, just with different chemical steps. And the steps are, they're quite involved. And if you take undergraduate physiology, or if you take exercise physiology, or you study this, you'll actually learn some of the chemical steps involved from taking, in this case, in the aerobic pathways, protein, glycolyl, or glucose, or fats, and transforming the potential energy in these chemicals to ATP, which is then used for muscle contraction, generates a force. We apply that force over some distance, we have mechanical energy, mechanical work, and then energy is how fast work is being done, or how fast a force is being applied. And the steps are quite involved, and it's good to know those as a scientist, because it does sometimes gives us some insight in terms of why we're doing a particular test. And before I jump ahead, we have the anaerobic pathways. These pathways do not require oxygen to generate ATP. They don't need oxygen. You can hold your breath, and this anaerobic pathway will work just fine. The aerobic pathway, it needs oxygen, and pretty much it needs oxygen at the last step. In the last step of taking the chemical energy in these different fuels, ultimately is where oxygen becomes important, and we're able to generate ATP, which is again used in muscle force for muscle contraction. And as I said, knowing the chemical steps will sometimes help us identify or understand why we do certain tests. In this case, I drew out a couple of the chemical equations. So here we have C6H12O6. This is glucose. And if we take glucose and we add some oxygen to it, we can actually transform that glucose into carbon dioxide, water, and energy, ATP. And that ATP is what's used in muscle contraction. And what's important to know, or one important part of this to know, is that the amount of oxygen we use is the same amount of carbon dioxide created. What happens to carbon dioxide? Well, you just exhale it. What happens to water? Well, you just absorb it in the body. It can be used a lot of different ways in the body. And so for glucose, there's an equal amount of volume of oxygen used and carbon dioxide exhaled. And it's an important thing to know, because later on we're going to talk about respiratory exchange ratio, and that's a ratio between carbon dioxide exhaled and oxygen used. And when that ratio is 1, we pretty much point to glucose being the primary fuel to generate ATP. Now, fats can also be used, and this is just one example of fats, where we take a lot of oxygen, we exhale some carbon dioxide, we also get some water, and we get lots of ATP as well. I didn't put down how much ATP in each of them, but this generates lots of ATP. And if we look at that respiratory exchange ratio, volume of carbon dioxide exhaled to the amount of oxygen used, that number becomes lower. It starts to turn towards about a 0.8, where we're talking about fats being the primary fuel. Now, over in the anaerobic pathway, what's important is that one of the byproducts of anaerobic production of ATP is the production of lactate, or lactic acid. Well, one of the fates of lactic acid is that it's buffered. And when it's buffered, you actually end up with a lot more carbon dioxide that you have to exhale. And that's why when we talk about respiratory exchange ratios going over 1.0, that's because you have a lot of carbon dioxide being produced via aerobic metabolism of glucose, and then you add on to that the carbon dioxide that's resulting from buffering lactic acid that's being produced at the same time. So you get a number over 1 when you do VCO2 over VO2. So the point of me telling you that now is that there's a lot of information we can get about both the anaerobic and the aerobic metabolic pathways during running by measuring gas exchanges, where we can measure what's being inhaled and what's being exhaled, and we can understand quite a bit about how active these two pathways are. And one other point to note is that there's a lot more steps to processing a fat versus a carbohydrate. And there's a lot more steps of the aerobic pathway than the anaerobic pathway. So these pathways just take longer to generate ATP. So there is a rate limiting issue in terms of ATP being generated for certain intensities of exercise. All right, so let's talk about the measurement of VO2. Well, in the lab, we use a metabolic cart. This is anywhere from $30,000 to $50,000 piece of equipment, and the person breathes into a mouthpiece or a mask, and it's sort of like a snorkel mouthpiece or like a mask that you put over your nose and your mouth. And as that person breathes in or out, the computer measures that air flowing in and out of the person. And as the person exhales, the gases are analyzed for how much carbon dioxide is in that exhale, as well as how much oxygen is in that exhale. And the computer, the software can then calculate how much oxygen was used, knowing how much oxygen is in the air, how much was exhaled. That difference ends up being the volume of oxygen used. And so it's a very standard piece of equipment in an exercise physiology lab or biomechanics lab, where we're measuring the physiology, the metabolic pathways of running. And we get information about both VO2 and VCO2. And those are two important parameters from this type of test. Now, the way the computer works, the way the system works, is it's typically measuring breath by breath. Then in the settings of the equipment, we set it to output data every 15 seconds, every 30 seconds, or what have you. And so it's actually averaging breath by breath data over that 15-second window or 30-second or whatever window we put in there. And that's important to know because or you can output the breath by breath data as well and then process the data independent of what the software is doing. And so different time intervals that you export the data in. In this test, we actually exported the data in 15-second intervals. And then we do an analysis of the data based upon that 15-second averaging that the computer has already done. This is what the data will look like from a test like this. On the y-axis is rate of oxygen consumption in units of mLs per kg per minute. It's a rate. And on the x-axis, just time. Now, in this case, the client was running a set speed, and there was no fluctuation. The speed was reached somewhere right before this mark right here. We do need to be careful in an experiment how quickly we ramp up from no running to the speed that we are interested in testing. A lot of times what will happen is we'll ramp the speed up. If we ramp up too quickly, what happens is there's an overshoot in terms of the amount of carbon dioxide being produced when you're going from zero to something really fast. So we try to control the ramp up speed going from zero to something. And you can see that in rate of oxygen consumption, the speed is quite low here. Then the speed is being adjusted to the test speed. Ultimately, the test speed is reached right around this window, and then the runner settles into a pace. And what we look for in a test like this is we look for steady state. There's different ways to define what steady state is. It's never a straight line. It just never is. In fact, if you see a straight line in this type of test, probably something's wrong with the equipment. There should not be a straight line because there's little fluctuations in terms of the number of breaths within that 15-second window. Maybe there's subtle adjustments to running style, movements of arms, maybe a little different stride rate for some section. There's lots of things that can influence running time, even running on a treadmill. Now, running outdoors, there's even more factors that influence the ability to achieve steady state. And I'll talk about that in a later slide. But nevertheless, we can operationalize or come up with an operational definition of steady state by looking at a mean and a standard deviation, making sure that we're in roughly a flat line response. Like if I just draw a straight line here, you can see, in fact, I got that right here. You can see that there's probably an equal number of data points above and below that average value. And in this case, what we did is I ran the data through a program. I write the code in MATLAB, and I select the data from time 2 to 4.5. And I picked that middle window for a couple reasons. I already talked about this issue back here. We want to avoid trying to average this information because this is not indicative of steady state rate of oxygen consumption measurement. I also try to avoid the ending of the test too, because sometimes some weird things can happen. The person sort of knows that they're going to end, or they have a funny dismount before we actually push stop to the treadmill speed. And so I try to avoid the ending of the test as well as the beginning. And so I just take a middle window to get an average value that represents the rate of oxygen consumption for this running speed. Okay, now when we do this type of test and we're looking at running economy, we've got to understand the different factors that influence running economy. Running style is one. I've already mentioned a couple of these things. Stride frequency, stride length, upper body movements, any changes to any of these will influence running economy. We know that if you start running with a faster stride rate, for example, or stride frequency, stride rate is the same thing, your rate of oxygen consumption will go up for that given speed. And likewise, if you take a really slow stride frequency for a given speed, your oxygen consumption will also go up. And so we know that adjustments in running style will influence rate of oxygen consumption. And upper body movements, if you hold your arms straight or put your hands up over your head and you try to run, that makes it harder for that given speed. And so running economy is not a fixed number. There's lots of things that can influence it. Fitness and training will influence running economy. As we become more fit, we will become more economical for running a set speed. So if I do this test, if I did this test back when this athlete was not trained, running economy would likely be worse. That is, he would require more rate of oxygen consumption to run the same speed. Experience, let's see, I don't have that in here. Well, I got equipment here. Shoes, that's why we're doing this test. Added weight can actually make a big influence on running economy, especially if we add the weight to the distal aspects of the extremity. So shoe weight becomes a big factor. And we actually did some work looking at wet shoes as well, and whether or not that will influence running economy. Actually, we only did this testing on the impact characteristics of wet versus dry shoes at this point. Experience running in the shoes is also an important factor. Anytime we put on a new pair of shoes, anytime we run on a different surface, we will subtly or sometimes drastically change the way we run. And so we do need to give some exposure, a period of time where someone acclimates to the new condition. In this case, it's shoes. In this case, the client was familiar with the different shoes and had run in each of them before, but they were all brand new shoes as well, which is another factor that we need to be taken into consideration, especially with shoe testing, is if we have a shoe that's had 100 miles on it, that may perform differently than a shoe that has 500 miles of wear on it. Not only the impact absorbing characteristics, but also the wear patterns on the shoes may ultimately influence running economy. Other environmental factors, I mentioned surface, going uphill, going downhill, the camber or how tilted the road is when you're running. Altitude makes a difference, air temperature, humidity, wind. These are all environmental factors or things outside the body that can influence running economy. Now, that's partly why we do a test in a lab for at least this stage, is to try to control a lot of that. It's not a perfect control, but it is control. And if we did this type of test outside, we would be looking for the influence of changes in air temperature, especially being here in Las Vegas and testing during the summer. Age can be a factor. Fatigue can be a factor. And one of the things in thinking about this experiment and the results, I'll mention this later on as well, is we measured this athlete while he was fresh. He did not do a bike ride before this. He did not do a swim before this. Now, the results may be different if we look at what happens right after a bike ride or near the ending part of a 13.1. As fatigue starts to set in, maybe we change our running style. Maybe we slow down, and that change in pace can maybe influence which shoe is actually the best shoe for that person. And there's also a psychological factor that influences running economy. In fact, a graduate student some years ago actually did her thesis on the influence of feedback on running economy. And the idea was to get positive feedback. You're running great, your form looks great in one condition, and then say nothing in the other condition. Subjects ran the same speed in those two conditions, and running economy was actually better when you received positive feedback. It's a really a funny thing that the way our brain operates is if we're feeling good, we may actually run in a way that reduces running economy, that we become more economical. And so we can't discount the psychological factor. And when we're dealing with shoe testing like this, ideally, and I'll mention this again later, ideally you blind the subject to the conditions or the intervention. It's really difficult to blind someone to shoes because you need to see where your feet are going when you're running. Yes, we all look where we're going when we're running. Now, when we're running on a treadmill, our gaze will likely be up a little bit higher, but if we're running on the road, we're certainly looking down and making sure that wherever we're going to put that foot is a solid spot for that foot. We do that unconsciously, subconsciously, hopefully not unconsciously. So blinding subjects to the shoe condition is actually really difficult for something like this. We could also blind the experimenters, but again, it's hard to blind them. You could probably get the same color of shoes, but each of the shoes being different brands and different models, they are quite unique, and it's not too hard to pick a shoe out from a profile. All right, so let's talk about the performance test. The task, as I mentioned, was to measure running economy at a 70.3 race pace in 3 different shoes. The shoes were all advanced footwear technology, the foam, the carbon plate. There are unique features to each shoe, but they all fall in this same category of shoe. The procedures, we gave the subject time to do a self-directed warm-up, and then we would have the subject run 5 minutes in each shoe, and we repeated that twice. The measurements we took were rate of oxygen consumption, rate of carbon dioxide exhaled, and we measured heart rate as well. We also did stride frequency measurement by hand. Next time we do this, we're actually set it up to be able to do stride frequency using another instrument, so it's a little bit more objective and easier to get. And then we also measured rating of perceived exertion, which is just a subjective rating of how hard the exercise feels. For the analysis, we calculated the average VO2 and average VCO2 and average heart rate between minutes 2 and 4.5. This is what the data look like for all the shoe conditions. And the first graph is rate of oxygen consumption, mLs per kg per minute. VCO2, also in mLs carbon dioxide per kilogram body mass per minute, heart rate in beats per minute, and respiratory exchange ratio, which is that parameter I mentioned earlier. It's a ratio of VCO2 to VO2. VCO2 being in the numerator and VO2 being in the denominator. And these are all the 6 runs together, and this is just time on the x-axis. Again, the speed is held the same for each of these conditions. This first part is the ramp up of the speed, and then the subject reached steady state. Anytime I do an analysis of data, I like to visually inspect the data. In this case, I'm looking for that steady state response. If we start to see some increases in slope or decreases in slope, with VO2 or any of these parameters, start to scratch your head and say, wait, something's going on. This person's not in steady state. But in this case, for each of these conditions, the client was in steady state. And you can see how these are all really blended together. And as I mentioned, if there was going to be a difference between shoes, it's going to be really subtle. But even from this quick inspection, we're seeing all these data points sort of lying right on top of each other. But nevertheless, we do a little bit more analysis. Here's the 3 shoes, and presented in the order that they were tested. 1, 2, 3, 4, 5, 6. Rate of oxygen consumption in mLs per kg per minute. VCO2, again, rate, heart rate, beats per minute, and respiratory exchange ratio. This just ends up being a ratio of VCO2 to VO2, so it's a unitless parameter, and then rating of perceived exertion. So we're reading the first 3 conditions, and then we stop, get the mask. We often have to manage spit and all that, and just make sure that the equipment's still behaving at that point. And at that point, the client felt he wanted to redo the shoes in the same order, and that's okay. For a test like this, it's okay to blend in what the client wants and what we would do for an experiment. Now, what's interesting, I always like to do this when I collect VO2 data, is I like to have an expectation of what rate of oxygen consumption should be, and that way you can make sure that roughly my instrument's behaving well. And using ACSM's equation for predicting VO2 while running 10.3 miles per hour, we would expect about 58.75 mLs per kg per minute for VO2. Clearly, we're under that for all these. This is a fit runner. This is a professional triathlete. This person is more economical than your average runner. All right, so this person's already very economical. So trying to make changes in even the shoe may not really influence running economy, and that's what we're really seeing here. Is these numbers are relatively close to each other, and even if we look at the second run of 3 trials, we see these are really reasonably close to each other. Now, it's also interesting. Sometimes people, well, what we do is we do look for order effects, but in this case, VO2 actually improved for running the test speed of 10.3 miles per hour, less rate of oxygen consumption for the third condition. Then there was a break, and then it sort of flipped here. And so, this person's fit, and I wasn't too worried about fatigue, so I wasn't too bothered by taking this second run in the same order, knowing that we were going to go back and look at each data set individually. But what we see here is very little change in VO2. Even this entire band of VO2 is pretty tight. Heart rate as well, RPE as well. There's this weird anomaly here, 0.9, that there was more a tendency to move towards a carbohydrate as a fuel for this condition. And interestingly, RPE just went up just slightly, but these are all moderate intensities subjectively. Oh, so here I talk a little bit more about the order. We do, in an experiment, always consider that the order of conditions can be a confounding factor. And we have to worry about fatigue, we have to worry about experience, and just overall acclimatization to different conditions. And this is something that we always really put a lot of thought into in designing an experiment. Now, a lot of times in our experiment, as I mentioned earlier, we like to do a double-blind study, but often it's very hard to do a double-blind, and shoe testing is not easy to do double-blind on. We'd have to get with a manufacturer to design 3 shoes that looked nearly identical, but yet representing the unique features that each brand has, and that just is impractical to do. Now, if we do really worry about the order effect, we often will counterbalance, and this is what's difficult in this type of client type of research, is that if we're going to do a true counterbalance, what that means is every order is presented once. And so we would do 1, 2, 3, or shoe 1, shoe 2, shoe 3, shoe 1, shoe 3, shoe 2, and so forth. And we would actually need 6 different orders to cover all the possible orders of the 3 conditions or 3 shoes. If we did that with the subject and we ran the subject at 5 minutes each time, we'd be talking about an hour and 20 minutes of running. So now running at race pace, now what happens is we start getting into this length of data collection. Now we do start to worry that the ending conditions may be influenced more by fatigue than the beginning condition. So it's really this balance of trying to have a sufficient controlled experiment for this type of client work, and yet trying to get information that is specific to this person. In addition to looking at the metabolic parameters I've presented already, I also calculated energetic cost of locomotion, which you can then turn into the amount of calories used per distance. Remember, energetic cost of locomotion is volume of oxygen used per distance, but we can convert that volume of oxygen ultimately over to calories, which is a unit of heat. And when you look at calories per kilometer, given all the data I presented, were really subtle differences, or hardly any difference here at all. Really subtle changes between the calories, 71.6, 70.6, 71.1. And for our practical purposes, this is about the same. And you can say, well, maybe I need to adjust my race plan by 1 calorie every kilometer. That's just not practical. Even though we take some fuel with us, maybe it's in a form of a glue packet or something in a packet, we rip that open and it says, oh, it's got 90 calories, whatever it is. You try to empty that into your mouth, you're not going to get 90 calories. You're going to get something most likely less than that. And so, we need to sometimes when we're looking at practical information, we have to be very careful not to get paralyzed by analysis or paralysis by analysis. We got to be careful that saying, oh, 1 calorie difference between these 2 shoes, oh, I would go with shoe 2, definitely. We have to be really careful with our interpretation of these data. But for all, from a race perspective, each of these shoes led to about the same caloric cost for per kilometer. And to calculate energetic cost of locomotion, I use both VO2 and VCO2 to do that. So some of the takeaway points from this test. Again, this test was for a client. 1, the runner is very economical. He's a professional triathlete. He's very competitive. What's from a scientific perspective, we're always negativistic. We're always looking to disprove something. And in this case, I would say that none of the shoes would be considered bad from a physiological perspective. All right, none really stood out as saying, oh, don't use that shoe. And likewise, none of the shoes actually really stood out and said, that's definitely the shoe you need to wear. There's lots of factors that besides physiology that we'll go into or that we have to consider when selecting a shoe. The course surface, the elevation profile, the turn. So think about our test was on a treadmill, very controlled surface. The speed was set at 10.3 miles per hour, driven by a motor. When we're running outside, running on pavement is different than running on a grass course. A golf course, for example. A lot of our iron distance events will go through some type of change in surface, whether it be a golf course or something else. Elevation, running uphill, running downhill, shoes may behave differently in both those situations. And even on turning, we didn't test any change in direction. And, as you look at some course profiles that have lots of turns on the run, you may need to consider that in a shoe selection as something that's stable when you are changing direction. We also can't discount a placebo effect, that the shoe that I think works best for me may actually influence the outcome of the study. As I mentioned, psychology does influence running economy. Comfort, I tell runners all the time, you have to pay attention to comfort when you pick that shoe. Unfortunately, comfort is not something that is easy to measure. It's a very subjective measurement. But maybe if you're running in a particular shoe and you always get that black toenail, maybe that shoe is not the right shoe for you because it may not actually be comfortable. and you've got to account for some rubbing, or if you're getting blisters in some way, shape, or form, or hot spots in the shoe, those are signs of a shoe not being comfortable. And as I mentioned a few times now, how a shoe influences running economy at the beginning or ending of a run really will influence the shoe that you may pick. And so, if you're, and this goes along with pace as well, the speed that you run at may actually influence what shoe is best for you. So someone who's running a 10.3 miles per hour versus walking 3 miles per hour, the type of shoe that those two individuals need could be quite different. And so we just have to consider all these factors when we are looking at these takeaway points for this athlete. So from a sports science application perspective, remember, I always look at sports science from two lenses. One is, how do we help use sports science knowledge now to help an athlete, a coach, a team, an individual, what have you? And then the other lens is, how do we generate long-term knowledge? How do we generate these big ideas that can be applied to broader audiences? So for the athlete, in this case, this is a blend of research and questions that the athlete has. And what's interesting is, in working with high-performing athletes, such as this one that I work with on this test, the athlete may be looking for marginal gains. And so looking for a 1% difference may actually be a difference in place in an event, maybe the difference between winning and taking second place, or being off podium and being on podium. And so those marginal gains can be important to explore. And so with this athlete, I'd like to bring him back and do another test, another round of testing, and maybe a little different protocol to tease out some other aspects of shoe design on his running performance. Now, the key information for application right now is understanding that energetic cost of locomotion was pretty similar despite the shoes being worn. And so now he can plan his nutrition plan for running based upon that information. At least that's a data point to consider. And it's also important to know that the range of shoe choice that he has is quite wide between these three different shoes. They are all advanced footwear technology category shoes. So they all have some aspects that are similar, but they're all very unique in some aspects of design, from the upper to the way the sole is shaped and what have you. From long-term knowledge, this type of work really fits into the main hypothesis that shoe choice is not made on a single factor. In this case, it's not running economy. There's other factors that come into play. Some other work that we do in the lab, we look at impact forces during running, and we consider that as being one of the factors in terms of selecting the right shoe. That, again, is not the sole factor for picking one shoe over the other. We really have to take in a number of factors to ultimately identify the right shoe. And frankly, we don't have the algorithm, and that's why when you walk into a shoe store, the wall is filled with different brands of shoes, different models of shoes, different sizes of shoes, what have you. And that's because we all run a little bit different. Our foot's all shaped a little bit different. We have different experiences. We all have different types of running that we're doing. And so we need to pick a shoe for me as opposed to an average person in a research study. Okay, I hope that was helpful in terms of applying exercise physiology or looking at running economy to help an athlete, and then understand that parameter a little deeper. Thank you.